Hello everyone. Just now we are going on the fourth section of our virtual congress. Now we are going to listen the one of the live presentation of the APMAS Congress. Professor Plamen Dankov from Sofia University, Bulgaria. He's going to present us material characterization in the microwave range, another look to the properties of modern artificial dielectrics as an invited speaker. Professor Dankov, do you hear me?
Yes. Fine.
Yes, welcome again.
Okay, thank you.
You are welcome.
I will share the.
Yes,
I will
you can
share the
share.
screen. Yeah.
Yes, okay. I would like to remind that this virtual congress is recording again. If you are ready, you can start your presentation.
Yes, I think we are ready. Do you see the?
Yes, we can see your screen clearly.
Yes, clearly. Yes, okay.
Yes.
Okay, thank you.
Yeah.
Thank you very much. Okay, I can start presentation. Okay. Once again, I would like to thank for organizer of this conference to invited me to share this information with you, this presentation. I have a look on the Congress program. I am thinking that I am the only presenter in this area of microwaves, area of microwaves. This is quite typical area of characterization of material. And I will share my experience with this area because in the modern world there exists a lot of new materials and most of them are connected with electronic and electromagnetic applications. Here on the screen we can see the list of some of them. For example, reinforced substrates for electronics, textile fabrics, for wearable antennas and application, multi-layer materials, absorbers, etc. A lot of ceramics, semiconductors, ferrites, multiferroics, ferroelectrics, liquid crystals. Also the family of 3D printed materials, metamaterials, nanomaterials and carbon containing materials, polymers, thin films, and even biotissues as new materials. Of course, we have to have information for such type of materials, because most of you maybe are familiar with some of the methods. For example, microscopy, spectroscopy, microscopy, optical, scanned electron microscope, or other methods give very important information for the materials on the surface or subsurface structure. Spectroscopy is also a very powerful group of methods. Ultraviolet, visible light, Fourier transform, infrared, X-ray, etc. Here the information is more deep, for example, for chemical composition, for composition variation of balance between the crystal and amorphous structure, photoelectric properties of material, etc. Mass spectroscopy also information about the mass to charge ratio, etc. In the microwave range, the situation is something different. We have usually the next quantities, for example, dielectric constant, magnetic constant, refractive indexes, and effective conductivity of materials. Maybe you know the empirical Cole model, which show that dielectric constant of dielectrics fall between the value of at DC frequencies, at very low frequency, and in the optical range. How to obtain information for microwave dielectric constant? Three methods are important. Free space method, where the material is placed between two antennas, and we can measure the transmitted or reflected losses and phase to extract the dielectric parameters. Or material is incorporated into waveguide in the area of waveguide methods. Or material is part of a resonance structure, so-called resonance method. We can measure frequency, resonance frequency and Q factors, and also to extract the dielectric constant. However, here exists some special circumstance. Dielectric constant may depend on the wavelength. Why? Usually materials has some own structure, atomic structure, metal lattice, for example, here with length A, and we can compare this length with the wavelength. In the microwave region, dielectric constant is an equivalent value. Because we can compare this periodicity length with the wavelength. So permittivity in the microwave region is an integral parameter compared with the other methods, where in spectroscopy, microscopy, etc., where the information is more or less local. Here, the integral character ensure information for the material composition, also for the structure, character of inclusions of dielectrics, building blocks and their orientation, use technology, and many other information. As you know, according to microwave metamaterial concept for materials, dielectric constant and magnetic constant could be positive or negative for some material. For example, in plasmas, a dielectric constant could be negative. In ferrites, magnetic constant could be negative, and in the so-called double negative metamaterials, left-hand metamaterials, where the both constants are negative. We can measure all of them, but let's attract your attention to so-called anisotropy, different dielectric parameters in different direction. For example, biaxial anisotropy, where the materials can be described with diagonal tensor with three different diagonal values. In different direction, different dielectric constant in different direction. Most of the materials are in this area, in this branch of materials. Next, so-called uniaxial anisotropic materials with parallel and perpendicular dielectric constant. This is typically for the flat materials, substrates and polymers and other. And of course, near to isotropic materials, materials like plastics, injection molded dielectrics, forms, etc. We started to summarize this information 3 years ago, and on the Asia Pacific Microwave Conference, I presented a poster, university poster for materials characterization, and last month I published a review paper in Fermat Journal, where the editor is Professor Raj Mitra, material characterization in the microwave range, when the materials became composite, reinforced, 3D printed, artificially mixed nanomaterials and metamaterials. And here I will share some information from this review paper. For example, what is the anisotropy of mixed dielectric, how to measure, and several examples, reinforced substrate, polymers, 3D printed, and some meta and nanomaterials. Of course, there exists a lot of methods to mix two materials to build new materials, depending on composition. For example, series, parallel, mix it, disperse it randomly or uniform, etc. And using some known formula, we can evaluate dielectric parameters. Here we can see if you mix some two components with parallel or with series modification, we can find a different dielectric, we can obtain different dielectric constant or randomly mix it. But the given formula are not so accurate, because we can don't put here the structure of building blocks, etc. Several years ago, we have an idea and developed it. We can build the unit cell for building new artificial dielectric. To build some meta material structure, and to put this structure into the resonator, and to measure dielectric, to measure resonance frequency, and to extract the dielectric constant. You can see here if the mode has electric field in different direction, we can extract parallel, perpendicular dielectric constant, or some mixed values. We tested this method for example, for knitted and woven textile fabrics, for some metamaterials, and find out that if the electric field lie along some fiber, cylindrical fiber, for example, dielectric constant increase in comparison with the dielectric constant perpendicular to the fiber. This is important and give us idea how to minimize dielectric anisotropy of materials. There exists a lot of methods for measurement of artificial materials. We have two authors method. One of them is called two resonator method. Even at the moment, I am working nearby with this method to test new material. At the moment, after presentation, I will continue. We use samples put into two resonator with parallel or perpendicular dielectric constant, and can extract, measuring the resonance frequency and Q factors, can extract the corresponding dielectric constant. This is very good method to give us very valued information for many materials. More than 1,000 type of materials we have accumulated data for materials. Here you see the picture of several resonators for the resonance frequency from 5 up to 40 gigahertz and beyond. Examples for successful measurement are for not successful, and because we don't have success with resonance method for metamaterials, we develop another method, a broadband method, when we put the material over the planar structure, for example, microstrip line or coplanar waveguide, and measuring the dielectric losses and phase into the structure, can extract the dielectric constant, equivalent dielectric constant of material. This is also very powerful method for characterization of materials. And several examples to the end of the lecture. In our maybe 15 years practice, we measure a lot of materials and especially commercial reinforced substrates. they are very popular materials in the area of electronics. And during our work, we find out a different material near to isotropic substrates with millimeter and 5G application. Now producer pay attention to have similar materials with near to isotropic properties. However, the most typical case is the case for substrates with middle anisotropy between 5 to 11% anisotropy, difference between the parallel and perpendicular dielectric constant, which is the problem for the designer. And some of materials has very, very big anisotropy, more than 15-20%. Here, we can see a very useful comparison between the materials of two companies. One company present very good materials with controlled anisotropy. Another company with not so controlled anisotropy of materials. We, in our practice, we find a method how to minimize this property, uniaxial anisotropy of reinforced substrate. Everything depends on the type of oven fabrics, and we can see here different types, and how to minimize dielectric anisotropy. Our concept for using of anisotropic materials is based on the fact that we can replace the anisotropic structure with the equivalent isotropic structure. However, and this is an inconvenience, this equivalent dielectric constant depends on the type of the used planar line, microstrip line, coplanar waveguides, or strip lines, etc. And this, for the designer, this is not good. People who are involved with this now, the problem, and they ask a question: which value I can use to describe my substrate? Next example is also interesting. This is characterization for a new type of substitute for substrates, so-called flexible polymer substrates. And the example is connected with polydimethyl siloxane material. This is a flexible material with many electronic applications. People think that this material is isotropic with dielectric constant not too well determined, because they are using different methods. And we find out that the reasons this material to have a different dielectric constant with different using different methods is the small anisotropy of this material. The data are not published yet. I will try to publish soon, but this is quite unusable, quite information. We cannot believe that this material can have anisotropy, but we find out using some microscopy that this material has some porous structure and air fillet gaps, and maybe this is the source of anisotropy. When the electric field is parallel or perpendicular to the air gaps, dielectric constant is different. This is very good measurement. We use it two resonator method and the broadband method, and have obtained very good coincidence between the data. This is completely new data for this very popular material, and even we conducted a very interesting measurement, temperature measurement, and find out that anisotropy appear about the 0 degree Celsius, between minus 40 to plus 30 degree Celsius. This is also very new, and we have explanation. The porous structure is minimized at very low, at very high frequency. So if you may summarize for this material, information from different methods, and our method in the microwave range are coincided, and this material has more or less anisotropic properties, and this is quite new. 3D printed material. Also, a lot of people are using now 3D printing materials, but not so many of them now that this material, different similar artificial material, depending of the used unit cell to build 3D printed material, may have anisotropy. We find out in the case for prismatic unit cell that depending of orientation of prism, we can see very big anisotropy, and only in the case of cubic unit cell, anisotropy is small. Another example is for hexagonal unit cell. New interesting fact: dielectric anisotropy depend on the thickness. I can repeat, this is quite unusual. Dielectric constant depend on the thickness of material. This is also new, and only by microwave methods we can obtain this effect. We proved this effect by 3D printing material, for example, for stereolithography. And here in the last column, we can see that this is quite usual. It's a natural property of 3D printed materials, and also find out how to obtain isotropic 3D printed material, and which unit cell are suitable for this, because many people are producing lens for as antennas with 3D printed materials, and they need this material to be isotropic. Next example, very shortly, for aluminium porous Nordic aluminium oxide. This is also very popular materials and a matrix for building of metamaterials. If you put here into the pores of this material different inclusions, we can obtain metamaterial properties, and we find out a method to measure simultaneously of this material dielectric parameters and see effective conductivity of materials with covered coplanar waveguide. This is also new information. Dielectric constant and simultaneously conductivity of material. Similar effect we obtain for some graphene materials. For example, I have information here for graphene, but not the typical graphene single layer or few layer material. This is our example is multi-layer graphene, and very important, this is new information for N-doped graphene, nitrogen doped graphene. And we find out, especially for nitrogen doped graphene, behavior as epsilon near zero material, dielectric constant near to zero. This is also a good metamaterial. And again, not published data, but soon we will share this information. And finally, some information for negative measurement of negative dielectric constant of some metamaterials, so-called magnetoelectric effect, etc., etc. And in conclusion, I can say that microwave characterization of materials is very important, and obtained results for dielectric parameters, they depend on the structure, on the inclusion, orientation, and isotropy of material, and this information can be added to the other information from the local method, microscopy, spectroscopy, calorimetry, etc., etc. Thank you for your attention. Thank you.
Thank you, Professor.
Yes.
Your nice presentation. Yes, I want to ask all of our participants, do you have any questions? If you have any questions, you can write your questions to chat part, or please write the chat part about you have a question. We can open your system's voice and you can ask Professor Dankov your questions by yourself.
Yeah.
We can wait a few minutes.
Okay, if not a question, I can answer if you have interest in the microwave characterization of material. Thank you.
Yes, I think for now there is no question.
Yeah.
But if any participant want to ask any questions for your nice presentation, they can send you an email.
Okay.
Okay. Thank you.
Thank you. Thank you once again.
You are welcome. Paylaşımı kapatır mıyız?